The enthalpy of solution, it's also known as the enthalpy of dissolution. It's the energy change when 1 mole of a solute is dissolved in an infinite volume of solvent. When we say infinite volume of solvent, what this really means is it's dissolved in so much solvent that any further addition of solvent would not cause any change in energy. So effectively it's a very simple energy change. We take a solute and we put it into a known mass of solvent. Now this will make a different mass of solution. So in this case we have to factor in the mass of the solute when it dissolves in our solvent. Here at the moment we have the whole apparatus as 50.25 grams. If I'm going to add the solute, put the solute in, and then it will dissolve, and as it dissolves there will be an associated temperature change. The temperature may go up or it may go down. It's quite possible for solution enthalpy to be both negative, in other words exothermic, or positive, endothermic. If it's positive, the temperature will go down. Okay, so we need to know the mass of solute so that we can work out the moles of solute. We need to know the temperature, and the initial temperature, and also the final temperature, and we need to ensure that the solute is dissolved as rapidly as possible, as that will limit heat losses to the environment. The calculation is fairly straightforward. As I said, we need to know the number of moles of solute that we've dissolved. So we need the mass of solute divided by the relative mass of the solute. The energy change will be, the mass being heated, which in this case will be the energy change of the whole solution, because the solute will then be dissolved in the solvent and it will make a homogeneous solution. So we multiply the mass being heated, the mass of the solution, by the specific heat capacity by the temperature change, E equals mc delta T, as usual, to give us our energy for that particular mass or moles of solute. And then we factor in the number of moles by dividing the energy change by the number of moles to get the energy change per mole. And here's an example. If we dissolve 5.24 grams of ammonium chloride in 50.25 grams of water, the temperature changes from 20.2 to 14.1. This is an endothermic process. The total mass of the solution is 55.49. So the energy change will be the mass of the solution times the specific heat capacity times the temperature change. The mass of the solute is converted into moles, and then we divide the energy change by the number of moles to get the energy change per mole. The answer is positive because it's an endothermic process. Now we can represent this by a Hess's law cycle. In this particular case we've got the ammonium chloride crystals, which are a solid. We are turning the ammonium chloride crystals into a solution which contains ammonium ions and chloride ions, which are separated. Now this could be divided up into two energetic steps. The first step is we need to separate the solid ionic crystal, if you like, the solid ionic substance, into individual gaseous ions. So that step's called, in this case delta H2. It is the lattice enthalpy, because we're separating all of the ions in the lattice into individual gaseous ions. Then those gaseous ions need to be solvated into an aqueous solution. So in other words, each of these ions needs to be surrounded by water molecules, and we call this the enthalpy of hydration. Now in this case it's the enthalpy of hydration of ammonium ions and the enthalpy of hydration of chloride ions. So if we want to put this as a cycle is shown like this, that delta H1, this process, can go via delta H2 and delta H3, well then clearly delta H1 is equal to, or the energy change of delta H1, is equal to the energy change delta H2 plus the energy change delta H3. We have the equation delta H1 equals delta H2 plus delta H3.